This is our last class meeting for Chem 214. And today we're going to review materials for Exam 7. In fact, that label is incomplete. So let's fix it. This is electrochemistry. All right. So the format for this is going to be like the previous reviews that we've done. I'm going to pull up the review document from Blackboard, and I've selected several sample questions from that review document that I think will cover the full range of topics that we are trying to master in this chapter. In fact, your chapter is 20 in Brown. My chapter is 18 for reference. Okay, and the document, the particular document, is the one labeled version 2. There is a version 1, but I'm going to stick to version 2 simply because I don't want to jump around. We're good. So I'm going to share that document right now. And it's right here. There we go. That should be big enough for everybody to see. In fact, I could make it a little larger. Not that that'll make a whole lot of difference once I process the video. Is that too big? Kind of lost some of it there. That looks all right. Scoot it over a little bit. There we go. All right. So I assume that you split your screen, or if you're viewing this on the video, I will have already split the screen with me on the right-hand side and this document on the left, so that you can see problems worked out up here. All right. I want to do the whole first page to get us started. And let me move some things out of my way here. Okay, number 1. All right. For the reaction of sodium bromide and chlorine gas to form sodium chloride and bromine, the appropriate half reactions marked OX for oxidation, RE for reduction are listed as selections for A, B, C, D, or E. So those, you'll notice that some of them have coefficients. So we need to work from a balanced equation in order to do this. Now, we have learned a method for balancing redox equations, the half reaction method. But that doesn't mean you can't balance an equation purely in the old style with our budget. And that might even work best here because notice there are no oxygens anywhere. So you don't need that extra steps to balance the equations with added reactants and products. So let me show you how that works. Sodium bromide and chlorine gas. And that yields sodium chloride and chlorine gas, sodium chloride and bromine. We know this is a redox equation because that's an element and it ends up in a compound here. Or that's an element and it came from a compound, that's a dead giveaway. This is a redox reaction, aside from the fact that the problem says it is. Okay, so let's balance this. We should be able to do that without even setting up a budget. We've got 2 bromines here. We need 2 bromines here. We got 2 chlorines there. We need 2 chlorines there. So 2 sodiums, 2 sodiums, 2 bromines, 2 chlorines, 2 chlorines. We're balanced. Now we need to decide which one is the oxidation and which one's the reduction. All right, these are 0. This is -1, this is +1, this is +1, this is -1. Okay. So the oxidation reductions are taking place with the halogens. Sodium is a spectator. So the oxidation half reaction is actually, we're going to be with ions here. Right? This ion is a spectator, so it's not going to be in either one of the oxidation or reduction reactions. We're focusing on chlorine going to chlorine -1. That's a reduction. Oxidation is bromine -1 to bromine. So this is 2 bromines yield Br2 Br2. And the reduction is going to be chlorine yields 2 chlorides. Those are the oxidation reduction. And we know they're right because in order to go from here to here, you have to transfer 2 electrons. 2 electrons here and here. So we know that they're equivalent in electron transfer. Okay, so the oxidation step is the bromine. 2 bromides. And the reduction step is chlorine plus 2 electrons yields 2 chlorides. All right, so I left out the electrons. We have to lose 2 electrons here, and we have to gain 2 electrons here. Okay, so that makes it complete. That's why the answer is B. All right, that was number 1. Number 2. Okay, now for number 2, we do have some oxygens in there. So you could conceivably balance this equation by the half reaction method. But the half reaction method, in addition to balancing electrons, it will balance oxygens and hydrogens as acid or base. But the non-oxygen, non-hydrogen atoms are balanced even if you do it without the half reaction method. And since the question is X to Y ratio, so this X to that Y ratio, it's not going to change even if we do it by this quick method that I'm going to show you. So it's BO3 minus, the vanadate ion, and the SO2, sulfur dioxide, then VO2 plus, vanadium oxide ion, and the sulfate ion. Okay. I probably should have left myself a little headroom up there, but no matter. So which one's which? Well, we have to do oxidation numbers first. This one is a -2 for oxygen, and it has to be a +2 charge. Right? So how do we get a +2 out of a -2 balance? Well, a +4 and a -2 is a +2. So this one has to be a +4. This one is 4 minus a -2. 4 times a -2 is -8. We only have to balance 6 of those. So that's +6. On this side, we have -4, 2 times 2. So this is a +4. And this one is 3 times 2 is -6, which means -5 only balance +5. So now we have our oxidation numbers. All right, which one is the oxidation step? +4 to +6 is oxidation. All right, so that is loss 2 electrons per sulfur. Gain, this vanadium is a gain of 1 electron per vanadium. Okay, now how do we balance that? Well, we balance it with 2 vanadiums. Right? 2 here, 2 there, times 2 equals 2 electrons. So that balances the non-oxygen, non-hydrogen components. We have, for XY, we have 2 to 1, 2 to 1. Right? 2 to 1. This is 2. This is 1. So the ratio is 2 to 1. That answers the question without having to go through all of the steps of the half reaction method. Now, if there had been a different question, like, I don't know, what's the ratio of the coefficient of hydrogen ions to water molecules? Then we'd have to go all the way through the standard method. But that's how we get the answer a lot quicker. It's important to know what the question is so that you don't spin your wheels trying to answer the wrong question. All right, C. C is next. See, I better check these off as I go. 1, 2, and I have 3 marked. The following reaction occurs in aqueous acid solution. Okay? In the balanced equation, the coefficient of water is, all right, there you go. Now we've got to do it the half reaction method. So if we're starting with this one, NO3 minus, and let's see, these are all aqueous. That's why we don't have any states, because everything's in water. IO3 minus plus NO2. Okay, what's the oxidation? Well, we need our oxidation numbers. This one's easy. It's a -1. This one is -6 for all the oxygens. Hold out 1. That means this is a +5. This one is a -6 for all the oxygens. Hold out 1. This is a +5. Okay, and this one is -4 for the oxygens. So this one has to be plus 4. All right, now we can write our half reactions. Oxidation step, loss of electrons, -1 to +5. So we have I minus yields IO3 minus. This is +5. This is -1. Okay, reduction step. Reduction step, that's nitrate to NO2. This is +4. This one's +5. So we added 1 electron. Okay, 1 iodide on each side, 1 nitrogen on each side. Now we do the oxygens. 3 oxygens. So +3 water. That means 6 hydrogens. Okay. Then we have here 3 oxygens and 2 oxygens. So we need just 1 water over here. Right? 1, 2, 3. 1, 2, 3. But we need 2 hydrogens. Okay? Now electrons. If this is oxidation, the electrons are going to end up over here, correct? But how many of them are there? How do you go from -1 to +5? You lose 6 electrons. All right. Here we went from +5 to +4. We gained 1 electron. Okay. So now we need to balance the electrons. Right? We need 6. We only got 1. So there's a 6 multiplier here. So this is going to be 6 electrons, 6 nitrates, 12 hydrogens, 6 nitrogen dioxide, and 6 water. Okay? Now, the electrons cancel. And the question was, what's the coefficient on the water? So we don't need to do the whole thing. We just need to look at the water. There's 3 waters on this side, 6 on that side. Those are gone. This changes to 3. Right. So that's why the answer is 3. 3 waters. Okay? And if you're in the middle of a test and time is precious, you only answer the question that's asked. Okay, that was 3. Let's look at 4. Okay. All right. 4. The following reaction occurs in basic solution. Okay. When the equation is balanced, the sum of the coefficients is, this is one where you have to go all the way to the end in order to add up the coefficients. Okay. So we're going to start with this equation. F2 plus water yields O2 plus F minus. Right? This one is 0 oxidation number. This one is 1. This one's 0. This one's -2. This one's +1. That's just the way water is. Okay, oxidation step. Who lost electrons? Oxygen. It went from a -2 to a 0. So we have water yielding O2, 0 and -2. And the reduction is F2 yields F minus. It gained electrons from 0 to -1. Okay, let's balance. We don't have any non-hydrogen oxygens there, so we skip that one and come back to it. Here we have F2 and F minus. There's 2. While we're here, why don't we do the electrons? So if we go from 0 to -1, that means we had to add 2 electrons because there are 2 of them. How about this one? How are we going to balance this? Well, let's see. We've got 2 oxygens here. We need 2 oxygens here. But that makes 4 hydrogens, doesn't it? There we go. 4 hydrogens, 2 oxygens. Now, oh, electrons. We have to lose 2 electrons per oxygen. Okay. Now we need to bring this one up to 4 electrons. So that's going to be, see, I should have given myself some more room. We have 2 here, 4 here, and 4 there. Okay, now we can add them back together. All right, the electrons are gone. We have 2F2. We have 2 water on that side. Then we have 4F minus plus O2 plus 4 hydrogens. Okay, so that's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Everybody's accounted for. That's acidic solution. We need basic solution. So we're going to add 4 hydroxyls here and 4 hydroxyls here. So these become water and you got 2 waters here that cancel and leave you 2 waters here. So now you got 2 fluorine molecules, 4 hydroxyls, 4 fluorides, 1 oxygen, and 2 waters. Let's add them up. I can do it in my head. 2 plus 4 is 6, 10, 11, 12, 13. So the sum of the coefficients is, I'll get it right in a minute, is 13. All right, that was 4. Okay, that's page 1. Now we're going to skip to 7. Seven. Here we go. There. For the redox reaction, 2Fe2 plus chlorine molecule, dichlorine, yields 2Fe3 plus 2 chloride ions. Which of the following are the correct half reactions? Right. This is similar to the first one that we did. And we can use a similar method too. So 2Fe2 plus for number 7. 2Fe2 plus chlorine, except this one's balanced, I think. 2Fe3 plus 2 chlorides. 2 chlorides, that one's balanced. So we just need to split it into the correct half reactions. So this is 2 plus, this is 0, 3 plus, minus 1. This one is reduced. Right? So we had to add 2 electrons, 1 for each chlorine. That's reduction. Oxidation is, what's this? 2Fe2 plus yields 2Fe3 plus 2 electrons. 1 electron per iron. Okay, so let's find the ones that fit. Let's see. Fe2 plus, here's 1, 4. Right? And the other one is this one plus 2 electrons yields that one. Right? So it's 1 and 4. That's your answer. All right. Next one I've got marked as 8. So we just scroll down a little bit. To 8. How many electrons are transferred in the following reaction? Now let's see, is this balanced? 2 chlorines, yep. 6 oxygens here, 6 oxygens there. 12 hydrogens, 10 iodides, 10 iodides. That one is balanced. How many electrons are transferred? So 2 chlorates plus 12 hydrogens plus 10 iodides yields 5 iodine molecules and 1 chlorine molecule and 6 water. All right. The hydrogens in the water aren't involved. They're in the balanced equation, but not in the transfer of electrons. So this one is 0, and this one's 0. That one is minus 1. This one, 3 times 2 is minus 6. Minus 5 has to be balanced. This is plus 5. Okay? So how many electrons are transferred? If we're going plus 5 to 0, that is a gain of 5 electrons per chlorine. Times how many chlorines? 2. That's 10 electrons transferred. Now let's check ourselves. If we're going from this one to this one, we have lost 1 electron per iodine. How many iodines are there? There are 10. Right? So that matches. 10 electrons were transferred. Right there. All right, that was 8. Let's see what's next on my list. 11. Let's scroll down to 11. Okay. All right. So consider a galvanic cell, a battery, based on the reaction Fe2 plus dichromate ion yields Fe3 plus chromium 3 plus in acidic solution. Calculate the voltage of the standard cell carrying out this reaction. Right? This is acidic solution. Okay. Now, reading that backwards, this is standard cell. That means under standard conditions. So we don't have to use the Nernst equation. We just need to decide which one's the anode, which one's the cathode, and provide the math to support the calculation of an electrical potential. Okay, I think we can keep it really simple. Let's see, there's one of those, yep. And Fe3 plus chromium 3 plus. Now, in order to find the correct reduction potential, sometimes the reduction potentials have built-in other components, especially when you have them starting with oxygen like that. So let me see, I'm going to come back to 11. Right now I'm going to go to the end of the document to useful information. And there it is. So let's look at dichromate. Here we go. All right, there's the dichromate. There's your hydrogens, there's the electrons, and so forth and so on. And then the iron, Fe2 plus, should be over here somewhere. As a reduction, it would go this direction. Fe3 plus first. Oh, that's the wrong one. Here it is. Fe3 plus to Fe2 plus, this direction. Okay. All right, let's go back up to number 11. Actually, while we're here, let me write down the half reaction, the reduction potentials. For dichromate, it's 1.33. And for iron reduction, it's 0.77. Since we only have to do standard potential, then we don't have to actually know how many electrons are transferred. Right? If we're going from this one is reduction potential, then going this way would be oxidation. That's the anode. So we would take this one minus this one, .56 volts, because well, just to prove it, this is 7 times 2 is minus 14. Have to balance minus 12 plus 12. This is plus 6. So plus 6 to 3 plus is definitely a reduction. Right? So this one stays the same. And this one has to change sign. Otherwise, we won't have a positive value. So this is the way it goes spontaneously. And this is E0. Okay, so let me go back up to 11. Oops, too far. There we go. Plus 0.56. Right, so we didn't have to expend a lot of energy. We just had to write the equation and determine which one was the anode and which one was the cathode. And be sure that the reduction potential is in the table. And it was. All right, that's number 11. And I'm trying to do it the quickest way that you would need to do it for an exam. We're just answering the question. We're not trying to drag it out and teach 5 or 6 different points. Although I do that sometimes, obviously. Okay, the next one I've got is 14. 14, here we go. There. Okay. A strip of copper is placed in a 1 molar solution of copper nitrate, and a strip of silver is placed in a 1 molar solution of silver nitrate. Okay. The 2 metal strips are connected to a voltmeter by wires, and a salt bridge connects the solutions. The following standard reduction potentials apply. So for the silver side, we've got plus 0.8 volts, and for the copper side, we have plus 0.3 volts. These are both reduction potentials. Right? That's not the actual voltage. So you have to decide which one is anode and which one's cathode in order to say that. Now, we're looking for the false statement among these 5 statements. So we got to take each one in turn. Look, there's no 2 of the above, none of the above, all of the above. So each one, there's one of them that's false. Okay, so we just work our way down until we find the false one, correct? A. This is 14. Electrons flow in the external circuit from the copper electrode to the silver electrode. All right, in order to do that, they have to flow from the anode to the cathode. Because the cathode is the site of reduction, it needs extra electrons to do the reducing. So let's see what direction they're going to go. There's our salt bridge, right? There's our external circuit with our meter. All right. By convention, the electrons are going to flow this way. So this is the cathode. This is the anode. Now, how do we tell which is which? Well, the way I do it is I alternately change the sign on first one and then the other and see which one gives me, by addition, the positive value, because positive voltage is spontaneous. So if I change this one to negative, right, we get a negative value. So that means silver cannot be the anode. Silver has to be the cathode. So this is silver. That means this side is copper. Right? If we change the copper to a negative, then we get a positive voltage. So is A true? Electrons flow in the external circuit from the copper electrode to the silver electrode. That's true. A is true. How about B? The silver electrode increases in mass as the cell operates. Haha. Reduction does what? Reduction converts silver ions to silver metal. We're adding electrons to these ions at the surface of the electrode. That's where the reaction takes place. And they're plated out on the electrode as silver metal. So yes, mass of silver does increase. There is a net C there is a net general movement of silver ions through the salt bridge to the copper half cell. No, the silver ions are moving this way toward the electrode. So C is false. Right? We found our false one. Right? And if you're taking the test, that's where you stop. You found your answer. But if we started from the bottom, we'd need to look at D and E. Negative ions, D, negative ions pass through the salt bridge from the silver half cell to the copper half cell. Why would the negative ions travel from here to here? Because those negatives are moving out of this environment into that one. If they're moving, negatives moving this way, you have to replace them. Because what's going to happen here? You're going to produce extra cations, copper 2+ ions, and you got to balance the charge. So negative ions are going to move this way, right? This will be nitrate. So the nitrates will move through, and whatever other negatives you have in the salt bridge to balance the charge. So D is true. And E, some positive copper ions pass through the salt bridge from the copper half cell to the silver half cell. Okay, that's also true. So you got negatives moving this way, positives moving that way, because we're extracting positive charge from the solution to plate it on the electrode. So the positives has to be replaced. So copper migrates this way. Okay, so E is also true. All right, that was 14. There we go. 14, 15. Let's scroll it up a little bit here. Let's see, we're going to have 16 also, so we got both 15 and 16 together. Which of the following species cannot function as an oxidizing agent? Right. Oxidizing agent. What does that require? An oxidizing agent must be reduced. It causes oxidation in something else, means it receives electrons. It has to be reduced. So we look at the ones that are incapable of reduction. How about sulfur solid? Yeah, they can go from that to that easily. How about B? Nitrate, NO3 minus. Can it be reduced? Let's see, +2 electrons. Well, let's see. Oxygen is not going to be reduced. It's the nitrogen. So this is -6, -5 to balance, +5. Oh yeah, +5 can go to anything else. We can add electrons here. How about C? Dichromate, Cr2O7, 2-. We found out this one was +6 before. Definitely, it can be reduced. D, iodide. Is iodide going to take on even 1 electron? No. Iodide will not function as an oxidizing agent. And then manganate, might as well be complete. Manganate ion. So this is -8, -7 to balance, +7. Yep. Manganese +7 will reduce readily. So the only one that cannot serve as an oxidizing agent is, excuse me, that one. As soon as I can, there we go, the iodide ion. Okay, that was 15, 16. Okay, which metal, aluminum or nickel? Aluminum or nickel could reduce Zn2 plus to Zn solid. We want to say which one can do this. Right? So it has to add 2 electrons. It's got to be a reducing agent. It has to be oxidized. Right? And these are metals. They can lose electrons. Right? But what we want to know is which one, or maybe both of them. Right? So if this is going to be the cathode, then these have to be the anode, which means they have to reverse their charges. I mean, reverse their voltages, excuse me. Reverse their voltages, right? It doesn't matter how many electrons are transferred, because this standard potential is an intensity factor. 1 second. Kitty, 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 kitty. Come on. Come on, Nixie. Come on. All right. All right. So if this is going to be, and the standard reduction potential here is minus 0.76. Okay. For aluminum, it would be like this. And its value would be plus 1.66. For nickel, this, I think it's 2 plus. Yep, 2 plus. 2 electrons. And this would be plus 0.23. Okay. Now it's simple. We've established these, one of these as an anode. There's your cathode. So just add this one together with that one, and you get what? You do get a positive value, right? So this one would work. How about this one? Add that one to this one. You still get a negative value, right? So that one won't work. Only the aluminum works. Okay? That's how you solve that problem. 16. Let's see. No, that one's not marked. 17, 18, 19. I think these are all based upon the same reaction, but I'm going to skip over to 20. So I think to do 20, we have to balance the equation anyway to do 18, 19, and then 20. So we're going to go let's see, 18. Yeah, there we go. Yeah, this is taking too long. There we go, 20. There's your galvanic cell. There we go. Let's see. There's your galvanic cell with the standard potentials already given for you. What is the value of Q? The reaction quotient. Well, we can't write Q until we know the balanced equation, correct? We have to know the balanced equation. There's no two ways about it. So if this is 20, we're part of the way there already, right? Because we're given a balanced half reaction. Notice 1 manganese, manganese, 4 oxygen, 8 hydrogen, 5 electrons. Is that correct? Well, oxygen is 2 minus, so that's 8 minus total. Hold 1 out, that's 7 minus 7 plus for manganese. 7 plus to 2 plus is 5 electrons. That's good. Chromium is plus 6. Going to plus 3, that means we need 3 electrons, but there are 2 of them, so we need 6 electrons. Right? So each half reaction is balanced, but we haven't added them together yet. So now we need to pick it up where we modify the equations so that we can put them back together. And then once we get the completed reaction, we can take these values up here, knowing this one is the anode, this one's the cathode, and we can calculate our Q. All right. Okay, let's see, make sure I'm still centered. All right. So they're both written as reductions, but we know that the chromium side is the anode, cathode, excuse me. Or do we know that? Maybe this isn't written in standard format. So let's look at the standard potentials. How would you get a positive number from these two? The positive number would come if you change the chromium side to the anode and make that negative. So now we have to write the chromium cell, half cell, as an oxidation, right? So this is not written in standard form. The anode now is over here on the left, and the cathode is on the right. See? Okay. So we write the manganese side as is. Okay. And the chromium side, we invert the equation. So we have 2 chromium, 3 plus, and 7 waters. That yields dichromate plus 14 hydrogens plus 6 electrons. Is that correct? 3 over on this side, 2 on that side. This one has 3 on this side, 2 on that side. Okay, we're good. Now we need to balance the electrons. We have 6 here and 5 there. Evens and odds means what? Means cross multiply. So we have 6 over here times this one. And 5 over here times that one. Right? So that's automatically going to get rid of the electrons. 6 times 5 is 30. 5 times 6 is 30. Electrons are gone anyway. So this one is now 10. This one is 35. This one is 5. This one is 5 times 4 is 20. 2 and 5 is 70. and this is 30. Okay, this one is 6 here, and 48 here, and 30 here. So that means the electrons cancel. And then 6 manganese, and 24 water. Okay? Now let's cancel some others before we bring them down. Hydrogens. We got 70 hydrogens here, 48 there. All right, so these are going to be gone. How many do you have left over here? Well, let's see. That should be 22. Right? 22 plus this is 70. Okay. How about waters? Well, you got 24 waters over here and 35 over here, so that means 11. Okay. Now we can add them back together. This one plus this one and this one. Right? We got 11, 10, 6. That 11 means that we can't reduce it any further. 5, 22, and 6. So maybe I better write it out. So we have 10 Cr3 plus 6 MnO4 minus plus 11 water. And then on this side we have 5 Cr2O7 plus 6 manganese 2 plus, and then 22 hydrogens. So let's see, we have 1, 2, 3, 4, 5, 6 parts. 1, 2, 3, 4, 5, 6. Okay, all our parts are there. Now we need to write, we need to determine the Q value. All right, so I've got this one. I'm going to erase this top stuff so I can write the equilibrium expression. Right. So what's the equilibrium expression for this so that we can write the Q? Well, let's see. The Q is going to be, this is 2 minus, excuse me. This is going to be dichromate to the 5th power. Oops. My first mistake. This is not equilibrium. There we go. Then the manganese 2 plus ion to the 6th power. And then the hydrogen ions to the 22nd power. Okay? How about the denominator? We have the chromium 3 plus to the 10th power. We have the manganate ion to the 6th power. And we got water. What do we do with the water? Throw it out. Doesn't matter. All right. So let me check myself. Yeah. Before I go to all the trouble of plugging the numbers in, I want to be sure I got everything's kosher. Okay. So what's the dichromate concentration? Dichromate is 0.3. to the 5th power. Mn2 plus, 0.2 molar to the 6th power. Hydrogen ions. What is the hydrogen ion concentration in well, the concentration of the hydrogen ions is 0.01. Right? It's the same on both sides. Concentration is an intensity factor. So it's 0.01 to the 22nd power. Then in the denominator, we have this one, chromium, which is 0.40 to the 10th power, and then the manganate ion to the 6th power, which would be 0.1 to the 6th power. So 5, 6, 22, 10, 6. Okay. Now it's just, that's the hard part. If we did that right, then all we have to do now is calculate. So you need to know how to do these multiple powers. 0.3, and then I'm going to the 5th power. 2.43 times 10 to the minus 3. And the second one is 0.2 to the 6th power. Now multiply those together. And then 0.01 to the 22nd power. There we go. Now 0.4 to the 10th power. Divided into that one that I just got. And then also 0.1 to the 6th power. Divided into it. So I get 1.2 significant figures. 1.5 times 10 to the minus 41. If I did my calculations correctly. Let's see. Answer's supposed to be B. That's what I got right there. Okay? So that's the Q. Now, we're not given the K for this reaction, so we don't know which way it's going to move. But that answers the question anyway. I'm going to leave that there for a second. Let's see. I erased the number, didn't I? Which number is this? 20? Yeah, 20. Okay. So I'm going to find out what the next one is in case we need this information. Okay. 22 is based upon the same reaction. 22 asks, let's see, let me scroll down here. 21, 22. What is the cell potential at 25 degrees C as read on the digital meter? This is not standard conditions. Right? Standard would be what? Everything would be 1 molar. But we've determined the Q. There's the Q right there. Okay? So now we're going to do 22 using that Q value. How do I know? Because I know the Nernst equation. and it needs Q. It also needs the number of electrons transferred. Do we remember how many electrons were transferred? I think it was 10. No, 5 and 6, 30. I think it was 30 electrons. Okay. Don't want to erase the equation yet. Q equals 1.5 times 10 to the minus 41. And electrons equals number of electrons equals 30. So this is 22. And in order to use the Nernst equation, which is the actual potential equals the standard potential minus 0.0591, and that's in useful information. Right? Just scroll to the bottom of the document, and there it is. Or let's see, this is Chem 214. So that information should be in the folder with the exam. So be sure and print yourself a copy before you start your lockdown browser. Okay, and what's in the denominator is the number of moles of electrons times log Q. All right, we got Q, we got the number of electrons. What's E0? E0 is cathode minus anode. Right? So the anode is the bottom one, right? Chromium, that needs to be a negative 1.3, and then add the 1.506. So standard potential is going to be 1.506 minus 1.330. 0.176. Is that right? That's right. Okay. This is going to be 30. And this is going to be 1.5 times 10 to the minus 41. Okay. Now we can calculate E. All right. We take this one and do the log of it. Let's see. 1.5 exponent negative 41. Take the log. Now we need to multiply it by this one and divide by that one. 0.0591 times and 30 divide. And then we subtract it from this one. It's a negative number. Negative 8.04 times 10 to the minus 2 makes it positive when we apply that negative sign. So I'm just going to change the sign and add 0.176. So that's 0.2 0.26 volts. A quarter of a volt. That's not much, is it? E. There it is right there. Okay. So we had to work our way through that, through 20 in order to answer 22. All right. So let me check that one off. And we got about 45 minutes left, looks like. So let's move along here. We're going to skip down to number 30 next. Oops, too far. There's 30. Number 30. The following has a potential of 0.92 volts. So we have mercury, 2 plus hydrogen yields 2 protons plus mercury 1, right? Hg2 plus Hg sub 2, 2 plus ion means each mercury is plus 1. If the concentrations of the ions were 1 molar and pressure of hydrogen were 1 atmosphere, what does that mean? Standard conditions. Then E0 for the half reaction would be what? Okay, this is a test of knowledge to see if you remember the standardization of reduction potentials. You always measure a half cell against a standard hydrogen half cell. That's what this is. Hydrogen bubbling through into solution and into its own solution, actually, producing hydrogen ions. And then what it does is reduces the mercury. So the hydrogen becomes oxidized from 0 to plus 1. Mercury goes from plus 2 to plus 1. Okay. So then the E for the half reaction would be what? Well, we got to look at it this way. What is the cathode? The cathode is reducing mercury, right? Reducing mercury. So that means overall has to be positive. Correct? This is from mercury 2 plus to mercury 1 plus. Let's see, we need 2 of them. There we go. So when you pair that with the anode, which is the hydrogen electrode, you subtract the hydrogen electrode from that. So what is the hydrogen electrode? Zero. Subtract this one from that one, and you get plus 0.92 volts. Okay? There it is. It's not negative. If it were negative, this reaction would run in the opposite direction. Okay, that was 30. And let's skip down to, let's see, we're going to do a big skipping. There must be a lot of repetition in here. Skip down to 44. Here it is, 44. Okay. And we're almost there. Oops, too far. 44. There. An excess of finely divided iron is stirred up with a solution that contains copper 2+ ion, and the system is allowed to come to equilibrium, okay, whatever that happens to be. The solid materials are then filtered, and electrodes of solid copper and solid iron are inserted into the remaining solution. Right? What potential develops between these two electrodes at 25 degrees Celsius? Do we need a picture? Right. We've got iron stirred up in solution. Let's see, copper system is loud. Let me read that again. Excess of finely divided iron is stirred up with a solution that contains copper 2+. All right, we've got iron and copper 2+ together, and they're going to come to equilibrium. Then you're going to put solid copper and solid iron inserted in here. What's going to happen? 0 volts. The magic word here is equilibrium. Aside from the fact that these are not half cells anymore, right? It was allowed to react, went to equilibrium. So there's no way that you're going to get any voltage out of that. For 2 reasons. It's at equilibrium, plus you got everything mixed together. Why would the electrons want to go external? There's no point. They can just go bam, 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 straight across, do their thing, and done. If it weren't at equilibrium, they could do that. That's what they did to reach equilibrium, right? So in this case, 2 strikes and you're out. 0 volts. Right? That's why the answer is A. I guess you could call that a trick question, just to see if you're paying attention. 49 is the next one. Okay. So let me go to 40. Oops, too far. 49. Okay. We make a cell with an aluminum electrode in a solution of aluminum nitrate and a zinc electrode in a zinc nitrate cell. So there's 2 half cells. If you could increase the concentration of aluminum, which of the following is true about the cell potential? It would increase, decrease, remain constant, can't be determined, or none of these. All right. And it's okay to use the reduction potential table to answer this question. Otherwise, it can't be determined. Right? You need to know which one is which. So you've got a reaction with aluminum. Right? And there's a voltage. And then the other one is zinc. So let's go down to our table. Oops, too far. There we go. So let's find aluminum 3+ being reduced. And here it is right here. So there's aluminum 3+ at minus 1.66 volts. Okay. And then we have, what was the other one? Zinc. Zinc plus an electron yields zinc solid. Is that right? Nope. 2 plus. 2 electrons. So that's a mistake on this paper. All right. Let's see. Zinc 2 plus, zinc 2 plus, zinc 2 plus. Here it is, minus 0.76. Okay. So those are our reduction reactions. Now we need to do something with them. Let me go back up to 49. Oop, too far. There we are. Okay. If you could increase the aluminum concentration, which of the following is true about the cell potential? All right. So now what we need to do is we need to determine the balanced reaction and the Q expression. So which one has to be the anode and which one's the cathode? We need a positive for both of them. If we make this one positive, we still got a negative. If we make this one positive, then we get a positive overall. So this one, aluminum, has to be the anode. This is the cathode. This is the anode. All right. So this is going to be aluminum aluminum metal yield aluminum 3 plus 3 electrons at plus 1.66 volts. So overall, we're going to have, let's see, 0 and 9, 0.9 plus volts. That's E0. Okay. So the overall reaction is going to be 3 times this one and 2 times this one, right? To make the same number of electrons, which means N equals 6. 6 electrons. Okay. We might need that. Okay, so what's the overall reaction? Well, the electrons are going to cancel, obviously. So we have 3 zincs, and we have 2 aluminum metal. Yields what? We have 3 here, solid, plus 2 aluminum ions. Okay? So, all right. So what's the equilibrium? What's the expression for the voltage? Because the question says what? Which of the following is true about the cell potential? 49? Yeah. If we increase the concentration of aluminum. Here. Okay? Well, we need the Nernst equation, which would be here. E0 plus, oh, excuse me, I think that's minus. Yeah, minus 0.0591 over N times the log of this one. That's a solid, and that's a solid. They drop out. So we only need this one. Aluminum 3+ concentration. Well, actually, that was squared. And then zinc 2+ cubed. I think that's another mistake I've got. Yeah, that's a mistake. This should be 2 here. There should be 2 there and 2 there. Oops, wrong color. 2 there, 2 there, 2 there, 2 here. Okay. So now we have a measure of the voltage. This is going to be 6. So, 49. If you could increase the concentration of aluminum, which of the following is true? Well, where's our starting point? Our starting point could be anywhere, right? It could be anything. So we just pick a starting point. Let's pick standard conditions, like 1 and 1. Like 1 squared and 1 cubed, that's 1 and 1. So the log of 1 is what? 0. So this term actually drops out for E0 equals E when it's 1 and 1. Now, what if we increase this one to 2? 2 squared is 4, divided by 1 is 4, right? 10 to what power is 4? Well, let's see. It's 10,000. Well, I should have known that. Wait a minute. 10 to what power is equal to 4? Oh, no. I need to take the log of it. Excuse me. So that's 4. The log of 4 is 0.6. So now the value is 0.6. And as you increase aluminum, the log only gets bigger. So this value becomes negative. As you increase aluminum, you actually subtract voltage from the E0. So the value of the measured voltage decreases. That's why here, that is the answer. The measured voltage, the true potential, decreases. Now, if we looked at it in terms of anode cathode, right, the anode, if you increase the anode concentration, what is it going to do? It's going to try, if you increase this concentration, it's going to drive the reaction back this way in opposition to the spontaneous direction. So that also would decrease the voltage. You can look at it 2 different ways, either this calculation reasoning or Le Chatelier reasoning. All right, but either way, the voltage would decrease. I need to explain that a little better in the worked problems. So that's what I'll be doing. I need to to mark it. And we'll do an update on that one. Okay, that was 49. And we got about a half hour left, if I'm on time. Okay, so that was 49. Let's go to 56. Okay. 56. What type of problem do we have here? How many moles of electrons are produced from a current of 14.4 amps in 3.2 hours? All right, we're not even, I assume that this would be an exercise in electrolysis, but we're not even concerned with plating metal out. This is an intermediate calculation for how many electrons are you actually producing here. All right, we have to know our definitions. We've got a current of 14.4 amps. 14.4 amps, which is equal to what? It's 14.4 coulombs per second. That's a lot of charge. That's a lot of amperage. Right? So that's where we start. Let me put it over here. 14.4 coulombs per second. Right? Times what? Well, 3.2 hours, which is what? 3.2 hours. Well, we can't cancel seconds with hours. We need seconds. So how many seconds in an hour? 3,600 seconds in an hour. So hours cancel, seconds cancel. That's the total amount of charge in coulombs. We need conversion to moles of electrons. All right, coulombs and moles of electrons. So what's the ratio? 96,485. That's also in useful information, that conversion factor. That's the conversion from this many coulombs to a mole of electrons. A mole of electrons possesses that charge. Okay, there we are. That's moles of electrons. Now all we have to do is crunch some numbers. 14.4 times 3.2 times 3,600 divided by 96,485. So that's 1.72 moles. Now that we know the number of moles of electrons, we could, if we had the balanced equation, we could work that into a stoichiometry for the plating out of a given metal. It just depends on the metal, right? Does it take 1 electron for each atom, 2 electrons, 3 electrons, whatever it takes? Then we could use that in stoichiometry to determine how much of the metal is plated out. So that's 56. Let's see, we're going to skip down to 64. That's good. We're actually going to do it for this one. Goody goody. $64. So what are we doing? Oh, we're going to chrome plate a bumper or something. What mass of chromium? By the way, there's more to plating a bumper with chromium than just sticking a steel bumper in there and plating it. Chromium will not adhere well. You can form chromium on the surface of steel, but they're not compatible. Their crystal structure does not bind them together. So once you get your chromium on that surface of steel, it'll start flaking off immediately. What you need is something intermediate between the steel and the chromium that will bridge the gap, the crystal structure gap. And that's a combination of copper and nickel. I'm not sure which one they put on there first. I think copper goes on first. They plate copper, and then they plate a little bit of nickel on it, and then chromium will stick very well to nickel. Okay, that's beside the point. Let's get back to the problem. What mass of chromium could be deposited by electrolysis of an aqueous solution of chromium 2 sulfate for 145 minutes using a constant current of 11 amps? Okay, so we need our balanced equation. Cr2 sulfate. Sulfate is a spectator. We're interested in chromium only. So we need to know the oxidation state for chromium. So let's do that first. Right, is that a 3? Yep. So what's the charge on chromium? Well, look, this polyatomic is 2 minus. So 3 times 2 minus is 6 minus. That means you have 6 plus over here. That means chromium is 3 plus. Okay, so we know what chromium is now. Chromium 3 plus 3 electrons yields chromium metal. That's the reduction equation that's taking place at the bumper, so to speak. Okay, now that we know our stoichiometry, we say, all right, how many electrons are being supplied by this situation? 11 amps. So 11 coulombs per second for 145 minutes. Right? But that's 60 seconds per minute. Oops, sorry. Boo-boo. There we go, 60 seconds. It cancels these, that one, and that one. Now we need 96,485 coulombs per 1 mole of electrons. There we go. Now we can find out how many moles of electrons. So we have 11. We have 145 times that. We have 60 times that. And we have 96,485 divided. So we have 0.992. 0.992 moles of electrons. All right. So how does that translate to moles of chromium? Right, chromium solid. So it takes 3 electrons for every chromium, 3 to 1. So we divide that number by 3, which is 0.331. There we go. Now we just convert it to mass, right? I'm thinking molar mass. So what's the molar mass of chromium? We have to look it up. I don't have that one memorized. Let's see. Chromium is right up here. Right there. And it's 52.00 to 2 decimal places. So 52 times 0.331. I got 17.2 grams of chromium metal. Okay, and there it is right there. That was 64. Oh, that's it. We've got some short answer problems at the end, and those are good to work. But in the Blackboard testing environment, short answers are not desirable. If I put any short answers in there, I've got to individually grade them. And under the circumstances, I just made them all multiple choice. So you still have to do the same work as the short answer type problems, but you have to select then from available answers. So that's it. And we're done about, let's see, 14:59 would be 18 minutes early. Of course, it doesn't matter because there's nobody else here but me. All right. Take care of that. Now, this exam is only on chapter 18, my chapter 18, your chapter 20. And it's due by next Friday. There's no final exam. We didn't have time for a final exam. We just barely squeezed in a review for this last chapter. So there's no time for the final. So you've got till the 14th of May to do this exam. And it shouldn't be a problem because the system grades it for me. And there are only 2 students left in the class anyway. So if you need that time, you can take it. And I don't think there's a problem with opening up the exam. No. All my students are up to date, so these exams open in sequence. You have to complete the one before the next one opens up, and my students are good. So exam 7 is ready for you anytime you want to take it. All right, that's it. And I hope you have a wonderful summer if I don't hear from you before then.